Okay, so I will continue with next to leading order. I have a communication with some of you after the class, and I think probably what I said is too fast and not very clear. So how we do this? Okay, how we do the integrand reduction to get to the coefficient of d and d tutor or c tutor is basically this example. Okay, if we have a 2-2-2 process, okay, we have a box diagram multiplied four loop propagators. Assuming that we have these, okay, box diagram, then you know the numerator, right? For a given phase point, you can numerically calculate what is a given phase point, a given loop momentum. You can numerically calculate what's the numerator, all right? And then you know that how this can be decomposed into D0, 1, 2, 3, because right now we only have 4 propagators maxima. So D0, 1, 2, 3, D0, 2, tau 1, 2, 3 times 1. Okay, right now there's no D5, D4, right? So just 1. And C0, 1, 2, C, 2 tau 0, 1, 2, D3, because we need to exclude the 0, 1, 2, so that means I not equal to I0, I1, I2. So D3, right? And they similar C0, 2, 3, C2 tau 0, 2, 3, D1, right? Good iteration, the B as well. The B you have the two propagator matters, right? So we know this in the form of this way. How do we calculate it? Is first you set old d to be 0. You choose a momentum, loop momentum, could be complex, but make sure that all the d0, d1, d2, d3 are 0. So all these are 0 because they are multiply some propagators. So all these are 0. So only remaining the first term, right? So you calculate NL. You know these functions, how to calculate it for a given phase point. And then you know the function form, then you can solve in that D0, D1, D0, 1, 2, 3, and D2 dot 0, 1, 2, 3, right? So you know after you solve these, you can do the second term is to set 3 instead of 4. 3 propagated to be 0. Then, for example, 0, 1, 2 is 0. Then this is still there, but you know you have resolved these, right? But then all the D1, D2 are 0, right? So this is just not there. All the B is not there because you ask for 3 is not 0. So only remaining is D3 is non-zero, right? So then you can solve in C0, 1, 2 and C2 tau 1, 0, 1, 2, okay? So you can iterate it this way. I mean, one by one. So set to choose for the box is the same thing. So I hope it's explain a bit clear for you that how we get, integrand the reduction get to the coefficient, okay? So I back to this. So the numerator, as I said, in d dimensions, you can decompose it into the numerator, d-dimensional numerator, into a 4-dimension part and the remaining part. Numerically, yes. No, not analytically, yes.
It's not possible.
Yeah, I don't think it makes sense as well because it's probably too slow as well. Analytically, there's no, I think analytically there's no way to calculate that because it will be very complicated functions of these.
The solution is only, is it a unique solution or?
Sorry?
Is it unique? The solution is unique?
These expressions, I think.
You put all the data.
No. The box is unique, yes. The 4 point is unique. If you choose 4, this is unique, okay? Because you have a momentum, you have 4 components, so you have 4 equations. It's unique. It's just a 2, L plus minus. You can uniquely solve these. 3, then it's not. So you need to find a way which one is independent way. There are some paper by Lobeto, Petal. There's ways to do this. So this is because you have only 3 equations. It's not enough to solve all what is a loop momentum. You have some freedom to solve. Yeah.
So that's going to affect these coefficients. The C theta.
No, this is would not. I mean, this is just a number, but function form. I mean, this is just a number for any phase space point. This is a number. C tilde is function form is no. So it's like a d tilde. I mean, if you look at d tilde, the function form is exactly no, right? It's proved that. So d tilde is must be like this. Similarly, for C tilde, there's a function form is exactly no. Yeah. So I mean, any value you get, you must know resolve this number. Okay. So okay. So let me continue. Again, so let's say the numerator can be decomposed into the 4-dimension part and 4-dimension.
There is a R term, rational term.
Rational term, yes.
Where is it actually in the expression that you showed? Go back.
At the back, go back.
Yeah, here.
Here there's no rational term because we.
This is the numerator, right?
Yeah, the numerator, and numerator comes into dimension 4. You NL, no, you see, right? I'm not decomposing into the NL bar epsilon. Yeah. So in principle, you need the NL bar epsilon. Okay. So right now, numerator I decompose it in this way, and then I need to calculate this because otherwise I'm missing something, right? So calculate is a good thing. So I just need to define my rational term. It's just equal to this, right? Take epsilon to be 0 finally. So this is this is just I do the numerator decomposition, right? First term has been constructed way of the OPP way, and this one is just calculated. And the good thing is this one is only UV related. Okay. So for example, this is an example that you see that if you calculated ground to ground with top group, you can get to the full numerator, and then you performing algebra, you can get to the n tilde part, and the n tilde part is only dependent on L tilde squared. Okay, the d 2 minus epsilon dimension part, and then you integrate these, right? Integrate it gives you rational functions. It's not log dependent, log or polylog or this kind. So it must be. This is why it's called rational terms, because it's just rational functions in the external parameters and the momentum, right? So that means we have R2 term. You define according to this definition. We have R2 term of these, and this can be after I drop these epsilon external legs truncated, so I get the vertex Feynman law like. So in principle, I can get my Feynman laws because the R2 is only UV related. That means when you integrate this one, the epsilon in the numerator must cancel with integration gives 1 over epsilon UV. Okay, not 1 over epsilon IR. This is proved by Dinner in the some of his collaborators. So then you can get the Feynman law, like renormalization counterterm Feynman laws, right? For these for your QCD counterterms, so you see that the expressions all are rational expressions of P momentum and the mass external, and right. So so this is you can develop it.
This is always finite.
Yeah, this is always finite. It's because you know the numerator is always epsilon squared term. Epsilon term, sorry. L tilde squared. So it's an epsilon term. You must be numerator is already epsilon, then you divide by epsilon. So it must be finite. Of course, you have a.
The integral has some infinite divergence.
Infinite divergence will not contribute to this one. Yes, this is being.
The UV part.
Yeah, only the UV part. Yes.
I mean, this is for a general integral, no? If an
Yes.
integral has both UV as well as infrared divergences,
Yes.
then you have quadratic powers of.
Yes. Yes. I mean. Yes. Yes. But this is a.
It will not affect.
This is not effect. Sorry. This is not effect. This is not effect as being proved, but I cannot say in a few words why it is. Yeah, but this is being proved by the Dinner's paper, I think. Yeah. The R2 term. Why R2 term only related to the UV?
Yeah, it depends only on the UV.
Yeah. In principle, naively, you think that it should also depend on the IR pole, right? If you get to the IR poles. Yeah. So, okay, I'm done. So this one. So then another complication is actually in the decomposition. I a bit cheating you at the beginning because I decompose it into di, not in the di bar. Okay, because all the loop momentum is four-dimensional quantities, and the di can only also be the four dimensions as well, right? Because you lose the epsilon, 2 minus epsilon information here. So this is a way that is can be decompositions into the way of like this, okay? And this can be calculated directly when you do this integration. I wouldn't go to details how this can be calculated, but this just give you the point that this in principle can also be included directly into extracting the precision of extracting these coefficients, and this one, of course, not needed in this we called R1, okay, another rational term because of from the denominator, okay, and this denominator it can be systematically include OPP, and in TIR actually we don't need this because we directly integrate at the level of we need R2 because we need to calculate NL with L in the 4 dimensions. But we don't need because we do it directly at the integral level, so we can directly numerator. We can directly integral with NL, not N theta, NL with D0 bar, D1 bar. Directly integrate this to do the reduction directly at this level. Okay. So for TIR we don't need. So just the OPP integrand level. So then we go to the real. The real is I mean, for the examples, you already see that we see that the 3 parts, right? As I said, the 3 parts is virtual. You have a pose, and it's from a loop integral. Leo is from one body of the phase space integration. So you have minus a epsilon square minus b epsilon. So they cancel exactly. This is your issue. So typically, you can see that if you're looking at the PT of the whole system, for example, if Z production, you're looking at PT of Z at next to leading order, you'll see that Born is, of course, the delta function here, the blue one. And the virtual is also delta function, but very negative delta function because of the pose. And the real is you have a PT, now you have a PT dependent, non-trivially, and you could blow up. Right? That's infinitely large. So unless you integrate this region, this unresolved region, go to the PT go to 0, you will exactly cancel get the pose explicitly to cancel the virtuous divergence. So that's us. I mean, the good thing is we can understand because in general the phase space integration is very complicated, right? Especially if you're working in the D-dimensional phase space integration, you cannot use the Monte Carlo techniques directly because your integral is D-dimensional. So the good thing is we can find that the singularity of the real, in fact, is predicted by QCD is universal. You just are looking at where this singularity comes from even also from our previous example, you will see that this one is from, for example, if your emission of gluon, its singularity is from this one internal propagator is unshared. Unshared comes from both, for example, the collinear, that is the gluon is emitted the same way as same direction as previous quark, right? So you can write into this way. That means in general, you can write in dz over 1 minus z and dkt squared and dkt squared. And z goes to 0, of course. So z goes to 1, of course, gluon is soft, right? And kt is go to 0, or the angle, theta angle is 0, it goes to the collinear limit, right? So this is the two limit. And these singularities can be understood, can be cancelled from the virtual, for example, these diagrams, okay? It's gives exactly minus sign of this one, okay? Sorry. So that means the cancellation happens. I mean, in principle, we cannot calculate with a given final state. That means I calculate Diejet production. I cannot only calculate Diejet. I'm at next leading order. I must ask for another ground radiation in my something, right? Another ground radiation in my final state in order to cancel my divergence. So then we need to define the inference safety. It's very important. Keown theorem or virtue and Liu can cancel divergence is only available for the, not for all the observables, only available for the inference safety, safe observables, okay? So that means in a fixed order calculations, observable must be inference safe. That means not sensitive to emission of the soft or collinear partons. Parton means gluons and quarks. So that means observable, given observable, if you ask for I and J is momentum is collinear, it's not, no point. Once here. Collinear, then it's just go to put your two particles to be together, to group these, right? So they are same quantity number, okay, if you collinear region. And if you go to PI1 is soft, it's just to remove this particle, okay, in your observable. So this means that, I mean, formally definition of the IR safety observables. So these are a few examples. If you think that the number of ground is not inference safe because you just simply emit another soft or collinear ground, you have increased the number of ground is 1 by 1, right? And the reading PT or energy particle is not inference safe. So think that is it not soft or collinear unsafe? Okay? In fact, it's collinear unsafe. I just gave you the answer because you can imagine that the leading particle, right? The ground, if it's leading, but if you're splitting into two ground, collinear ground, right? Then they share the momentum, so you are not reading anymore, right? So it's very sensitive to your ground is splitting or not. So it's not collinear safe. And the color in a given cone is not IR safe, actually, okay? Because easily that it's not soft safe because in the given cone, in the given cone, if you do not, of course, you jet clustering, you will have you ensure that you have a collinear safe, IR safety. But you imagine that, I mean, just you're looking at naively write a cone around the one particles, and to see the colors inside the cone, it's not because you have a soft singularity, a large angle soft singularity, just go outside your cone, right? And it's carry away the color, right? So it's not soft safe. However, some others as safe. For example, if you're looking at transfer energy sum, it's safe, right? If soft, it doesn't give you 0 of the transverse moment energy sum, or collinear, you just sum them together. So it's the same quantity. It's collinear or not collinear, soft radiation, not soft radiation, then change your quantity. So its transverse energy sum is IR safe. So the atomic example, I gave a atomic example. I mean, actually, we already see example previously, but right now I will give you general ideas by view atomic example. Is assuming that my phase-space integration can be casted into the one-dimensional case. I just integrate one-dimensional dx, okay? I integrate y, my x go to 0 to 1, okay? Okay, here is 10, but 10 to minus 1, I write, okay? It's convenient. So my r, the real imaginary element squared, is, no, it's, sorry, I shouldn't put the delta function here, sorry. There's no delta function. It's just I for x pi over Rx times x, okay? So you see that x goes to 0, it's divergent. It's inferent divergent, okay? Then you have phase boundary is 0 to 1. And then my virtue is the delta function, so it must be located at x goes to 0. Huh? So this is the delta function proportion, but after I integrate my loops, it gives me b over 2 epsilon IR plus virtue. Of course, I have normalized these. So for the IR safety, this means if I take x equal to 0, my OX times Rx is equal to O0 times Born. Okay? This will ensure your inference safety to make sure that your pole can cancel. So then I can calculate it. So I do my virtual part, and then I integrate my phase space dx go to 0 to 1, x2 minus, again, I do the dimensional regularization. And then I integrate this one and put your expression, my expression r with alpha x pi rx over x, no delta function, okay? Into this, and then put my expression there. You will see after you integrate it, you will get b over 2 epsilon I r o 0 plus a plus function. Okay, this is the final plus function I defined because I used this. Okay, because you see that I have 1 over x, so I multiply this. It can be x minus 1 minus 2 epsilon, and this one can be decomposed into the delta function part, singular, and the plus function part and the epsilon terms. Of course, high epsilon term, I don't care. I just neglected it. So then I go to this expression, and then you see that my pole just cancel b over 2 epsilon and minus b over 2 epsilon. I just pole cancels. I remain O0v plus the plus function final piece. Okay? The final plus function means for any test functions, I write in this way. I subtract my end point, okay, to make it finite integration with x. So in general, the phase space integration over real matrix is very hard. Okay, it's not like this simple case. So you need dedicated approach to develop, not dependent on the process. One way is to do the phase space slicing. In fact, you can imagine that the divergent part is x go to 0, right? So let us just divide my phase space integration into 2 parts. One is x go to 0, at just 0 to delta. Delta is very small. And then delta to 1, okay? And then I integrate my phase space integration into 2 parts, 0 to delta and delta to 1. And 0 to delta is single port. And this one I can do some approximations. I can approximate it to integrate them because Rx function in general is very, Leo matrix elements squared is in general very complicated. But in delta go to 0, I can do some simplifications in my matrix elements, right? And then I just neglect delta point term, delta square, delta linear terms, all these kind of terms. I just neglect them, right? And then I can integrate analytically for this one about the bond, okay? So it's just O0 delta minus 2. This toy example, of course, easily to integrate. And then the remaining delta to 1 part I can integrate because finite I can integrate numerically. So I just set the epsilon to be 0, okay? Because finite right now it's no single. And then the first term, the single region, I integrate analytically. Then it gives me 1 over 2 epsilon IR minus log delta. Okay, so remember that log delta you need to be infinite small because you neglect delta is a linear port, right? And 1 over delta part, this phase space part, this phase space part, you can integrate numerically. Okay. So the finite can be integrated numerically, and the things is here you remember that the power delta terms are suppressed. We actually did not calculate them because it's very hard. And there's also large logarithm cancellation if delta go to infinite small because you need to make delta infinite small, otherwise your delta power term cannot neglect it. But then if you go to infinite small, you have large log. And large log will cancel after you integration with these finite piece, right? Numerical integration. So these large numerical cancellations have a big problem, probably gives you to do the numerical integration. So another approach is subtraction method. It's very mature in negative leading order, and they are also quite developed in negative leading order. The general idea is very similar, regardless negative leading or negative leading order. The general idea is very similar. Is you just find a simple function to mimic my Leo matrix element. My Leo matrix element is too complicated, but I'm trying to find a more simple function that I can analytically integrate it, but also have a feature that I match exactly same inferred singularities as a real matrix element, right? So if I take the two particles collinear, I get the same value as the Leo metric element. And I take the one momentum to be soft, I also get the same Leo metric element to be identical. But if not, then they are not the same, not necessary to be same. So then what you need to do is you calculate this previous one, then you plus this term, the subtraction term, and minus this subtraction term. So just add 0, right? So this piece, you can, because S function is much simpler right now, so you can integrate analytically. Of course, it's not really very easy, but it's still much easier than the integrated Leo part. Bar the over factor is born, okay? Over factor is born. And this one, right now you have matched exactly singularity, so they are finite, so you just integrate numerically, right? You drop the epsilon equal to 0 directly to do the integration numerically. So both are finite right now, and this analytically can be integrated, and this is integrated numerically in 4 dimensions. So in our example, toy example, we just take S function is B times theta function, okay, cos x over x. So we match the singularity. It's much simpler than my Leo metric element, right? And but I mean, I have freedom because I can cut any cos. I mean, it doesn't matter because the only requirement is I match the singularity region, right? S function. So let us use OX equal to O0. That means if I calculate directly the cross-section, not some convoluted cross-section with some observables, just cross-section, then you can see that you can integrate this simple one is 1 over 2 epsilon plus log cos. Right now, cos, remember, cos is not like a delta. Cos can be actual value, so not necessary to be small value. So cos can be 0 to 1, okay, any value. You can check that your subtraction constant term. Your final result is independent of cos value you're choosing, okay? It's a strong cross-check as well. Because you add something and subtract something, just add 0, so, right? So here, there's no approximation, because nothing is loosed. You do not drop anything. There's still numerical cancellation because you have R minus S. In single region, you have numerical cancellation. But numerical cancellation is much more mitigated because numerical cancellation at the integrand level before you do the phase-space integration, right? So this is much helps you to do have a good numerical convergence to do to perform phase-space integration. So the mass formula, come back to this. Mass in general is my Born virtual real. I simply add real integrated counter terms minus the counter terms, right, to do the n plus 1 phase-space integration, right? So the general feature is a subtraction counter term you should construct. You can construct any one if you can. Then you propose a new subtraction method. The only thing is you need to exactly match a single region of a single behavior of a real metric element, and it can be integrated numerically in a commutative way here, and it can be integrated exactly in d-dimensional for one bounded phase space point, one bounded phase space, right? And it is process independent, should be process independent, over a factor of Born metric element, okay? The reason is this can be doable because of all the single structure is universal in the gauge theory and the QCD. For example, if you're looking at these diagrams, in fact, if you take the linear limit, you just goes to Born metric element squared times a universal split function has been introduced in pattern shower lectures yesterday by Liv. And soft singularity, same thing. You can see that it's just a Born, but color-linked Born, so it's IJ, not IJ. The color, there's a color transfer, times universal PI, PJ, these acno factors, okay? So all the process, they should be the same for the in the gauge theory or QCD, okay, in this form, in the single regions. So there are two proposed approach, widely used approach. There are other alternatives, but not so widely used. So widely used typically is a dipole, Catani-Samo in the 1996 on the dipole subtraction. And there's also by the fission increase the signal in 1995 called the FK subtractions. And dipole actually is being most used method, and FK is a bit less used method. The thing a bit different is the configuration of constructed ace functions or the counterterm functions is different. In dipole, according to the soft configurations, that means based on you have the spectator and the emitter, so it's recoil taken by one parton. It's scaling if you have enough enough external legs, QCD legs. It's scaling as n third, okay, n squared, n cubic, sorry. And FKS is based on the collinear. You can imagine a collinear configuration. So it's a bit faster because it's if you have enough external legs, it's scaling as n squared. Okay, so FK is a bit more efficient in principle, and this is both are general. Okay, are general has been proved for simple and complex processes being worked. And there are different packages on market like dipole is made dipole, auto dipole, Sharpa using the Halak NAO, and FK subtraction using mad graph, and also in the Paul-Hague box, Paul-Hare. Oh, I mean, yeah. So several tools is being used. Most use the dipole, but also some use FKs. So I will not introduce dipole, but I introduce FKs because MATGraph implements FKs, and they are typically yield the same result. There's nothing different, right? I mean, if you the better different, but the result is always the same. So the FK subtraction is your real metric element. If you take inference limit, you can in principle have factors, prefactors like 1 over Ci over 1 over y, 1 minus yij. Ci is just a particle, for example, gron, the energy over your total center mass of energy, right? So Ci go to 0, go to divergent, right? Because momentum goes to 0. And yij is two partons angles, right? So cosine angles. So if you go theta angle, ij goes to 0, that means yij goes to 1. It's also gives you single, right? So the main idea is you need participation in the phase space in order to have, in each part of phase space, to have at most one soft and one collinear singularity, because you want to avoid the overlapping singularities. Okay, so that means your metric element, real metric element times your n plus 1 phase space integration is equal to, I just add the Sij function. Sij function is 1, sum of 1. So I just times 1, right? I don't change anything. The Sij1 I can choose the functions. Okay, there are some ways. I mean, if you want to know the concrete form of these, you can check the MAD-FKIS paper or original FKIS paper. There are different forms used. But what they need satisfied is if Pi, Pj collinear, you need to make sure that Sij equal 1. That means O and Sij equal to 1 because you want to only keep these phase space partitions, right? If Pi, Pj, Pm, Pn is not, or in other words, if Pi, Pj equal to 0, okay, either collinear or soft single region, Sij must go to 1, or the Si others is 0, because it's 0, okay? It's in another way. So that means I only keep, if you go to single region, I only keep that phase space point. That phase space part, okay? Because in order to make sure that in my phase space, each partitions on my phase space, at most, I have one soft and one collinear singularity. And then use plus prescription to subtract the divergence, right? You know that each phase space point regions, you can, after subtraction your divergence, you can go to plus functions, as previous toy example we ever showed, right? So this is the definition of plus functions, and times Sij, you see, and the sum of the ij. So that's why we can use direct take the plus function intellectually. So then you have 3 counter events. One is a soft counter events. That means Ci goes to 0. There's collinear counter event is Yaj goes to 1, and soft collinear counter events. Okay, and then this is one. I mean, if you're looking at the plus function, you see that this is my Leo emission hard event, right? And this is my counter event, right? That means I need to Ij y go to 1. Y go to 1 means I'm my collinear counter event, right? So my Leo integrations must be match element, the hard event, subject my collinear counter event, right? Then in this region would be collinear safety, right? So I don't go to details. So there's a few things, details. There's also momentum mapping or this kind of thing. I wouldn't go further, but you remember that there will be some there will be cancellation at the integrated level. So for any IR safe observer, do not ask for infinite resolution to numerical integration, because then your numerical integration you may have a trouble. So your being is so close to the single region, you will be strong fluctuations, right? So, okay, so I'm going to next-to leading order plus pattern shower. All these previously is all the building blocks for the next-to leading order calculations. And this is a loved picture, and I would like to change something, but finally I didn't get a better one. So, in principle, from here, all right, we have calculated next-to leading order. We want to go to the particle level descriptions or exclusive descriptions. So actually has been a bit talked in the LIFS lectures. Pattern shell will evolve hard patterns by emitting strong quantum down to a more realistic final state, right? So then to do the hadronization to make of the hadrons. And this is very important because it's resum the large logs appearing in phase space corners and to give the exclusive event descriptions. So they have complementary different phase space regions to the fixed order calculations. So only also at next to leading order, we see that there's singularities, right? If you're looking at the toy example, there's if you x go to the 0, you will see that 2 infinite numbers. So if you follow the Olivia's lecture, you see that if I want to unweight my events, I must know my match element max value of on my match elements, right? But here we do not, because our max value is infinity, right? So that means at next to leading order, without matching to pattern shower, I cannot unweight my events, right? So unweighted events I can only do after matching to pattern shower to make all my regions, phase space regions, there's no infinite values, okay? So this is in particular important for experimentalists because the experiments, they have very time-consuming simulations, especially for detective simulations with giant fall, right? This takes so long time. So unweighted events is very important for them. And next to leading order in particular is inclusive. So it can be fully differential, but you always need to integrate the unresolved Coulomb, right? So you don't know what's the momentum of unresolved Coulomb. But it provides the first reliable estimation of the rate and uncertainty, scale uncertainty in particular, right? As examples we have shown previously. So the how to do this at leading order is quite simple because leading order we know that we generate match events according to my match element. I just do the shower, right? Nothing special. However, at next to leading order, we have some double countings. The double countings is both from Born and virtue because it's Pseudocode you contain some virtue, and this is being if you calculate virtue in your match element and you also count into your pattern shower Pseudocodes, then you double count the pieces. Also the Leo emissions, right? If you have in the calculation of next to leading order, I also ask Leo emissions, and you will see that Leo emissions they share the same overlapping of the parts. Of course, they are not exactly identical, but they have a same part of pieces, right? So topologically, they seem the same diagrams, right? But they are not identical, but they are overlapping parts. You need subtraction. So further, if you go to Leo, you do the shower, same thing, you have a further double counting. So double counting, you have a double counting, do double countings between Leo emission, pattern shower, between virtual corrections, and non-emission probability with pseudocode factor in pattern shower. So let's see why there is a double counting in the more formalism way. Okay, so if assuming that you do the same way as next to leading order pattern shower, next to leading pattern shower as leading order pattern shower, okay, it's wrong. Okay, but let's see why it's wrong. So you have a Born, virtual, and then n-body phase space integration. So you just match your elements. You generate the match elements according to these. Imagine you can generate that, and then you do the pattern shower with this pattern shower operator according to my n-body final state. And then you do, according to your real port, generate the real port n plus one body events, and do the pattern shower again, okay? What happens? Okay, so these are pattern shower operators. Because of a unitarity of pattern shower, of course, if you're expanding these pattern shower operators, or pseudocode pattern shower operators, you should gate the next to leading order, total inclusive results, right? Plus high orders, of course, you're allowing. But at next to leading order, you only have one collect result. So let's expand. So my pattern shower match, the operator, is my two pseudocode. I just simplify there's no scale dependence, okay? Because it's irrelevant here, but relevant for POHIC. But so there's two pseudocodes, right? Naively, it's delta A plus delta A one emission. So there's zero emission and plus one emission, right? And then you can expand your pseudocode, right? It's just split function, alpha S over 2 pi split function. Naive way. Reality, of course, it's not only these, but naive you can imagine in this way. So expand my exponential into alpha S order, because alpha S squared I don't care, because I just up to the next to leading order. And then you gate these, okay? Remember that there's integrate here, okay? 1 minus integration, and there's no, okay, in the second piece. Then expand these. We do see that we have leftover. This is my next to leading order. The first line is my next to leading order, right? This is what we needed. So that means we needed to ask for this with 0, right? However, it's not, right? Naively, it's not, right? If you do this naive shower, it's not. Of course, you have high orders. But at next to leading order, they are not. So you don't recover next to leading order cross-section. Oops. So what you can do, okay? So let's see that in the MC at NL formalism, there are two ways, one MC at NL and one POHIC. In MC at NL formalism, double counting can be queued by just using the Monte Carlo counter terms, assuming your pseudocode is this, okay? And then you expand your shower, operators into some order alpha S, right? Neglect alpha squared. Then what do you need to do? In fact, what we see that we have something additional terms come from these, right? Born times d phi 1 and integrate of d phi 1, okay? And right now, I actually add back, just minus this one, in fact, okay? So I just minus 1. So you see that it's my integration. I just add integration of Born. And then here, n plus 1, so no n plus 1 body, right? So I minus this one. So I just add back, then I recovered, right? I just subtracted, right? So then you do the expansion to the same exercise. Then you can see that, okay, I expand, I cancel previously. I mean, my counter term and my Monte Carlo counter term introduced it will cancel my pseudocode from pattern shower, right? Double counting piece. So this is just the next to leading. I recover the next to leading order cross section for MC single plus high order, of course. So the MC counter terms has some remarkable properties. First, about the double counting you already see. And then matching, also, this is matching infer the singular behavior of the Leo matching element. Okay, then it makes your weight is not infinite anymore. It's making it possible to generate unweighted events. Okay, but up to a sign, because you subtract something, so it could be not positive anymore, right? It could be positive and positive and negative. So you just weight that is could be plus and minus. So you have some cancellations could be happen. And there's also smooth transition matchings between potential and match elements. The reason is what you constructed in the inference region. You see that from this example. In inference region, the real part goes to 0 because we matching exactly singular. So in the inference region is 0, right? And if in the hard region, of course, the match element Monte Carlo quantum is goes to 0. Okay, Monte Carlo goes to 0, so we just the real emissions. Okay, so in the hard region, it's just go to recover my Leo match elements. So there's a smooth transition. This is the TT bar pair of the PT total PT. You see that fixed order completely blow up. Well, it's, because binning effect is not really blow up, but you see it's very strange behavior. But you see that with the negative leading order pattern shower, Herwig 6 is a blue one, and you see that at the and this is the yellow one. The yellow one is leading order per pattern shower. You see that at the Pseudocode, at the PT much smaller, the single regions, it goes to close to the shower. Okay. And in the real part, you goes to the Leo match element, next to linear calculations. However, the MC counterterm is pattern shower dependent. So then, for each pattern shower, you need to construct your Monte Carlo counterterms, right, to the corresponding matching, right? So then you MC SNO pattern next to linear pattern shower, you have two type of events. One is S events, and one is hard events. That's Leo part, right? Leo part minus constant. This is very naive things, okay? But in this case, do you think that, do we still need FKS constant terms? Do we need a subtraction again? Anyone knows? Do you think since our MC constant term is exactly matching the Leo part, seems we don't need, right? In practice, we need. The reason is Monte Carlo quantum is very complicated. It's very hard to integrate analytically. So this one is very hard to know. Okay? So you need, in principle, you need to do is your sub minus S here to integrate numerically plus S analytical integration. Okay? So that's a practice, of course. So that's a practice really FKs. So why in math graph, if you run next to linear pattern shower, you still need the FKS counter terms. Okay. So with the important point is, as I say, is we should, because we added the Monte Carlo counter terms. So right now, if you do not do shower, if shower operator is just 1, it's not physical anymore, right? You're missing something. So without shower, next to linear event from the Lejeune event generated from math graph, it's not physical anymore. You cannot use that directly. And also, if you use a generated Lejeune event from the from some shower configuration, and you use it to other, for example, you do the P8 some shower. I mean, in P8 way, you generated MC SNO and Lejeune event, and according to this Lejeune event, you cannot use it into Herwig shower. Right? Because they are different. Right? So, I mean, unless you know all the details of the shower, they are exactly the same, right? You need, I mean, if you want to avoid double counting, you need to do the same matching and do the same shower. Okay? So remember that do not blindly use as leading order, blindly use the LG event file that is generated without showering. So another way is Pohik, in fact. So what Pohik do is it try to modify the Pseudocode for the first emission. So they change in the pseudocode. Right now, I put back the scale, or scale squared, I mean. So it's pseudocode is the real metric element over Born times one body face-to-face integration. And my operator, my shower operator right now is delta tilde and delta tilde qt, and with emission, allowing emission coding to the real, okay? Remember that here is not Q0, T, okay? So this is, T is where the R and B is calculated, okay? The scale. The reason is, right now, unless you have the T, then you integrate the T dt here, okay? Integrate dt here, you will get unitarity, get 1, okay? If you do the Q0, then you wouldn't get 1, okay? So right now, Poincare cross-section is simply B plus V plus d phi 1R and d phi n times I tilde, the shower the Monte Carlo operators, shower operators. So then you can see that you can verify that this is needed T, because if you integrate Q0 T to Q0 to Q, this is this is, you know, right? Just differentiate these. Then you will get 1 minus delta tilde, right? So this is consistent with this term. So integrate this one with dt, Q0 to Q1, you get 1 unitarity, okay? So T integrate goes to 1. So then the Poincare formalism is B plus V and R times in body times, I tilde, right? You can expanding, okay? So expanding to see that, exercise to see that there's no double counting anymore, okay? You just recover next to leading order, okay? So how to interpret the Poincare formalism? So this is the global k factor times Born, okay, effectively. And this is my modified pseudocode for the first emission, okay? And this is, of course, the first emission, right? This is pseudocode, right? Vetoed. So know that I think I wouldn't go to the details. Know that when matching to pattern shower, one has to veto emission harder than T, right? Because T is where you calculate your metric element. That's hard. Should be counted into metric elements, right? So in Poincare, it is interpreted as transfer momentum, okay? Even with showering for different ordering variables, okay? And the formalism should be modified if you showering in angular ordered pattern shower in order to keep the coherence. There are two method approaches are formally equivalent at next to leading order, but there are, in practice, there are many differences, okay, between the two. So the difference, right now I can write my next to leading pattern shower into single formalism, okay? Uniform formalism for both MC10O and the pattern shower is my Born. This is the Born is B plus V plus RS, a single term, okay? This is single term of one body phase space times my pseudocode, right? Delta S and one emission in body plus my Leo finite port, okay? In plus one body. In the MC10O, you can verify that yourself. You will see that RS, the soft single port, the single port is we just set B plus times the Monte Carlo constant, okay? Pseudocode is the Monte Carlo pseudocode, okay? In the Poincare formalism, the single port is F, it's a damping factor, times the Leo metric element, and the final piece is just 1 minus F times R, okay? In default, you can say that F is just a 1, okay? That means all my Leo matrix goes to the single region. But it can be tuned in order to suppress non-single part of the R, okay? Here's example, in fact. So if one can take h squared over h squared plus pt squared, okay? Then if you can see that there's a pt of Higgs production. The red one is next to leading on the next to leading logless summation. MCSNO is blue dashed, and Poincare is is purple dashed, right? It's purple line. Okay, no, not purple. What to say? What to say? Magenta. Okay, yes. And this is just no damping. Damping f equal to 1. Okay, f equal to 1. And this is another color. I don't know how to say. This is a damping factor is 140. There's a damping factor. You see that without damping factor, f equal 1, that's all geometric elements go to single region. Actually, Pohig has overshoot the fixed order calculation a lot. Okay, but damping factor, things you put back. I mean, you not put everything in the single regions. Okay, PT go to large, infinitely large, then f goes to 0, right? So you have a very small of everything geometric go to the finite piece, in fact. So damping factor will drop these and to make sure that it's similar as MCSNO and analytic calculations. Okay, so that means in Pohig it's very important to tuning the damping factor. So there's comparisons of two approaches. There's both advantages and disadvantages, pro and no. So MCSNO, as you say, the pattern shower is usually is not exact in the software limit. So MCSNO needs an artificial smoothing. Pohig, it is fine. I mean, because it's take his Sudokov, right, for the first emission. And the good thing is for MCSNO is do not exponential the non-singular part because it's just rely on the pattern shower, Monte Carlo, what they do, right? So we do not, MCSNO do not do the arbitrary exponential for the real part. And Pohig is doing some kind of exponential for the real part. So this is not proved, of course. And also you see that in the Pohig you have the real over Born, right, in the exponential. So Pohig needed to deal with the Born 0. It's a problem if sometimes you calculate Born, you get some phase points that Born escapes 0. It would be troubling to calculate real over Born, the Sudokov. MCSNO do not have this problem. The good thing is Pohig has independent from pattern shower, and everything is not. Okay, and Pohig do not have negative weight, and everything have a negative weight because Pohig is just multiply something, right? Both are automated. MCSNO is automated via MCSNO approach. Sharper is MCSNO approach. Pohig box is a Pohig box approach. Okay. How much time 0? Okay, then it's perfect. Huh?